Well, good afternoon. It's glad you managed to make it with all the changes and plans and so on. Um, Circumstances beyond my control kind of caused them, so I apologise for that because I know your time is important. So, what we're going to look at today is the beginning of chapter 8. I think I should warn you up front, this is going to be tricky. The last two sections are going to be the hardest ones that I would suggest you're going to have to deal with. I think part of the problem is that there's a lot of nitpicky steps to what you must do to make this thing work. And we're essentially, chapter 8 is we're going to look at hypothesis testing of proportions of various kinds. So that means hypothesis testing where there's a percentage involved. And then chapter 9, we do the exact same thing again, but we look at confidence intervals and hypothesis testing and all that fun stuff. But we look at it where the information isn't a proportion, but the average. So it's the same theme, but from two different perspectives. So I think I'm going to try and start by describing the process by using an example of how it would be used. So I want you to imagine we've got a story here. And in this story, we had, in the past, we just knew, because we've collected a lot of data on it, that the percentage of people who smoked, percentage of adults who smoked was, say, 51%. That was in the past. So we're assuming that that is information that was true back then. Now, a social scientist has decided that he wants to see, because he's got a feeling that that percentage today is much smaller. So what that scientist did is, he got 1,003, just to be awkward, 1,003 people, a nice random sample with all the usual things in place, and he found out that only 40% of them were regular smokers. So that's my story. In the past, it was 51%, but today, according to our sample at least, it's gone down. So the question is this. Think of it like a court of law. Is there enough evidence to prove that the percentage of smokers has reduced? Now, if you think of it as a court of law, so you have a process you have to go through. Superficially, that's a good answer, isn't it? 47% is less than 51, and that is definitely evidence that the percentage has gone down. But would you want to convict someone on that evidence? Because what you've got, you kind of think in the analogy of the court case is that even for innocent people, isn't there some features that are evidence that they could have done it, right? They had a motive, whatever the other evidence could be. But what we have to figure out is a way that we can come up with a process that every scientist, every statistician has agreed on beforehand that will allow us to say, this now counts as evidence that it has reduced. And you can go to learned magazines and you can send your evidence away and it'll get published and people will take account of it and say, oh, that's interesting. So how do we do it? Well, there's a number of phases. Step one is collect the data and verify we can conduct. What we are going to call this process is hypothesis test. So we're already entering into some jargon words. So we're going to collect the data and verify we can conduct a hypothesis test. Right, well, I've collected a sample of 1,003, 47% of the people said yes. Let's look at what we mean by that. There were 3 things that have to be true before we can even start the process. And they're all to do with the sample. So the first one is in no particular order, but I guess I should do it. Sample is independent. Second one is sample is big. And third one is the population is large. A little bit cryptic here, but according to my story, I collected a nice random sample of 1,003 people. There's nothing weird going on, so I'm going to say yes. The sample is independent and it's good to go. Is the sample big? Right, when we talk about is the sample big, remember we had to calculate this thing called NP and N1 minus P. Remember those guys? NP and N minus 1P. You do the same thing. And are they bigger than or equal to 10? 51% is definitely bigger, and the other guy is definitely bigger. So when you're doing these calculations, that's the guy that you use. You don't use your sample, you use that guy. Now, is the population large? I am going to assume that America has a very big population and therefore it's done. Step 1 then is finished. Collect the data and verify that we can actually conduct a hypothesis test. These questions better be yes, or else the question's finished. Just move on to the next question. Right. Step 2, phase 2. Set up the hypothesis. Right, so, oops, I'm going to, wait a second, I'm going to stop this and just mute everyone because I'm getting some feedback. I'm assuming you might be as well. And here we go. Are we all looking at the big paper again? Like a yes?
Yes.
Perfect, okay. So here's the first thing. When you set up a hypothesis, there's a guy called H naught, or H naught, and a guy called HA. This guy is called in the jargon world the null hypothesis. And this fella here is called the alternate. In my story, I'm trying to see or prove that there's enough evidence to prove that the new answer for P is less than 0.51. When you do hypothesis test, the sample, the P hat, has nothing to do with this. It's always to do with that guy. Now, in this particular case, the null hypothesis is that nothing has changed. So the null hypothesis is always nothing has changed. Okay? The alternate is the one that you're trying to see if there's evidence for it. In my story here, the evidence is has it gone down? Now you notice that the number I use here is the same number that goes there. So what we're saying is, it's either nothing's happened, it's still the same as it was 20 years ago, or the alternate is that it's gone down. And P is representing the population percentage, population proportion. That's step 2 done. Step 3 now. We're going to calculate the various statistics that we need. Right. I already know this guy, but sometimes I need to calculate it because the story might be, 482 people in the sample said they didn't smoke or something, right? So that's one of your guys. There's another guy you're going to calculate called the standard error. Now, there are two possible candidates for the standard error. One of them is right and the other is wrong. One will give you the number that you should use and the other will give you a number that you shouldn't use. Now, they both look almost identical. There's one major difference. In this standard error, you use that number. In this standard error, you use the 0.47. The one that we should always use is this one. I never use that one. So let's see what that's equal to. The square root of 0.47 multiplied by 0.53 divided by 1003 this time. I'm just going to do this off screen for speed. So it's the square root of 0.47 times 0.53 all divided by 1003. And the answer I get to 3 decimal places is 0.0157. So there we go, 0.016. Is there any questions about what I've done so far that you want me to maybe clarify?
How come it's the p hat number instead of the regular p?
Do you know the answer to that?
No.
I made a mistake. That's the answer to that. After telling you which one to use, my brain decided to use the wrong number. But there is a lesson to be held here. You see how easy it is to use the wrong number. I mean, you just casually scan and you see a decimal and you use it. So it's a very good question, and the answer is not very nice. But with a little bit of jiggery pokery, I can fix it. So it's going to be the square root of, this time 0.51 multiplied by 0.49 divided by 1003. And the answer I get is 0.158. So 0.0158, which actually ends up being 0.016. So by sheer good luck, my mistake happened to be an answer that was pretty darn close to the same one and ended up rounding off to being the same one. But that's luck. Don't rely on luck to save you all the time, because it probably won't. So I'll go back to my earlier question. Now that I've fixed that mistake, and it was just simply a mistake on which number to use, are we comfortable about the 3 steps to this process so far?
Can you go back to number 2? I came in just as you started that step. So
okay, so let's try and explain what this step is. Number 2 is you set up the hypothesis, and essentially the hypothesis is going to be an H0 and an HA, and it's going to be talking about the population. So H0 is that the population proportion is 51. In other words, people who smoke, it's still 51%. Nothing is harmed. So your null hypothesis is always going to be P equals some decimal. And the decimal that you use depends on the story, but there'll be some number that says, in the past, this was true. Or in the old drug, this is the percentage. And that's the guy you always make equal to 0. And that guy, the H naught guy, is called the null hypothesis. And then
Okay.
the alternate is that it's different. In this particular case, we're trying to see, has the population percentage gone down? Is it less than 51? Can you imagine another story where we think it might have increased, in which case P will be greater than 0.51?
Okay.
There's actually 3 versions of it: less than, greater than, and the third one is it's not equal to it. And that one is, I know it's changed, but I'm not really sure how. It might have got bigger, it might have got less. I just know it's not the same as it used to be. And that's the third one. That's P not equal to 0.51.
Okay.
Right. So, we good?
Yeah. So then when you got to step 3, you were saying that we would never use P hat.
Not in that case. You use P in this case. And eventually I did. P hat is one of the statistics we need. P, standard error using P is another statistic we need. We still have some more statistics to calculate. I told you this question is going to be fraught with lots of little nitpicky things. And believe it or not, we're probably only about halfway through right now. There's a lot more to happen.
Wow. Okay.
Right. So right now, we've got that part. I'm still calculating some statistics. The fourth one is going to be get the z-score and p-value. Wow. So let's talk about what those things are. The z-score. It's got a nice little formula. I know it's quite a long time ago. Remember you got z-score and it was things like x bar take away mu over standard deviation. Remember that z-score? Vaguely?
Mm-hmm.
Yeah. Right. The textbooks describe it like this. Now, who is P naught and who's P hat? Well, I'll put at the side here who they guys are. P hat's the easy one because it's been called P hat all the time. It's a sample. It's still that 47%. This weird guy called P naught, it's just a name so we know where to look. P naught is this decimal here. Now, I guess they could have just called that P take away P hat over the standard error. I mean, they could have just, that would have worked, wouldn't it? You just make P equals 0.51 and you'd be happy. The reason I'm using P naught is because when you look at the textbook and you look at some of the examples, that's a very common way of writing the formula. So I want us to get comfortable with it. So you see this little guy here? That's just the name we give to the value of P. It's called P naught. Now, in this case, it's 0.51, take away 0.47, divided by a standard error of 0.016. Now, I'm going to leave this page and show you something on my calculator. And it's an easy mistake to make. So I'll probably end up doing it as I'm showing you. Now going to share the calculator. Right, now that calculation was 0.51, take away 0.47, divided by 0.016, and that guy's called the z-score. So I'm about to do it wrong, deliberately. 0.51, take away 0.47, divided by 0.016. Where have I gone wrong? Because that's definitely the wrong answer.
The 0.016 part?
No.
Nope. Try.
Yeah, you did. Thank you for trying.
parentheses around the
That's
top
it.
part?
Yeah. You need to do the top guy with parentheses, or as I call them, brackets. We call on that guy.
Yep.
Right. Now, I can tell when I'm doing this, when I've screwed up, if I forgot the brackets. Do you know Z-scores from a way back in the day, where you calculated the Z-score of something happening? And the numbers that you get are essentially standard deviations away from the mean. So when you look at the particular one, the numbers for a Z-score typically are in the range -3 to 3. If you see anything bigger than 3 or less than -3, it's like winning the lottery kind of number. It's very rare to see that. So in this case, I've got a 2.5. And yeah, my mind is somewhere else today. It's not your lot's fault. I just have some other unconnected issues distracting my poor brain. So we're going to get this guy called the p-value now. And in this case, it's what's the probability that you get a Z-score greater than 2.5. So if I draw a little picture, there's a Z. You remember the Z's go 0, 1, 2, 3 kind of thing. So 1, 2, 3, it's roughly about here. So if you want to visualize what the p-value is, it's what's the probability that you, in this case, you get a Z-score bigger than that. And we're now going to jump back to the calculator, and I will show you what that would look like on our calculator, because it's just easier to show than it is to say it. Right. We're going to get the normal CDF. Okay. Anybody, what button do I press to find normal CDF?
The blue button, and then the verse, and you go down to number 2.
Got it. Remember that guy? Now, if you want to get a number bigger than 2.5, it's 2.5 to, you know, lots of 9s, right? Now, this is a Z-score. The mean of the Z-score is 0. Can anybody remember what the standard deviation of the Z-score is? What number it is?
Isn't it 1?
Yes. And then you paste it. And the answer I get is 0.006. Now this is what 20 odd minutes, and we haven't even finished one question. So you know this guy is going to cause you a lot of grief, right? So when you start doing it, it'll be a lot quicker because there won't be all these pauses and jumping around, but it'll still take you a fair amount of time to do a question. So there we are right now. So we get the Z-scores and the p-value. Ready to continue? What's left? Step 5. Use the significance level to decide if there is enough evidence to prove your statement. There you If you remember what this statement was, we want to see, is there enough evidence to prove that the number of people who smoked has gone down? Well, superficially that looks good. But there is a kind of ruler that we use, a kind of guide to deciding it. There's a number called the significance level. It uses the Greek letter alpha. So that's what it will look like in the textbook. And it's going to be a very small number. In fact, it's typically one of these numbers. This is called 1%. This is called a 5% significance level. And this is called a 10% significance level. So if you ever in the future read reports or analysis on a hypothesis test where someone said, hey guys, here's evidence to prove what I've just said is true. Here's evidence to prove that it's gone down. You will have associated with that entire testing process a significance level. It's either 1, 5, or 10. And this is the test. If your p-value is less than the significance level alpha, then you have shown that there is enough evidence to prove your statement is true. So if your p-value is smaller than that significance level, then you can then say with a fair degree of confidence that the percentage of smokers has definitely gone down. Now they have a fancy jargon sentence that's like, you know, the lawyer was standing and the judge pronounces his sentence. This is what it looks like. This is what it typically gets said in the textbook. There is enough evidence to reject H0, which is that, and so HA is true. That's the same meaning as that. I'm just writing this down a little bit more English, but this is kind of the formal way that you do that. So you do a test. If your p-value is less than alpha, you've proved what you were after. You've proved that in this case it's gone down. What happens if the p-value is bigger than or equal to alpha? What do you think you do then? Any ideas? What do you think you might do then in that particular situation? Okay, this is what they do then. There is not enough evidence to reject H0. That's all you say. We're not saying that the number of smokers has stayed the same. We're not saying it's gone down. We're not saying it's gone up. We're just saying, look, we didn't find evidence to prove anything. And that is kind of the end of that question. Right, is there anything about that process that you want me to go over? Because all I'm going to do next is do another question a lot quicker. And hopefully a lot quicker at least. And maybe if you've seen two of them, you'll begin to say, oh, okay, they do this, they do that. And I'm getting the idea.
So we have to do these 5 steps every time we have a problem like this?
When you look at the homework, you only really need to do whatever they ask you to do. So for instance, the homework question might just say, find the p-value, and that's it. Or the homework question might say, prove that the initial steps are true, right? check these 3 things out. So not every question gets you to do the start to the finish. So it depends on what they ask, how much that you have. And a lot of the stuff I've got here is kind of verbals, just so you can go back and look. But can you imagine if you took away all the words, most of what you do is calculate things and get Z score and get a p-value. And so there's a little bit, you don't write down as much in the homework because of that.
Okay.
Okay. Right, time to do one more, because at the speed this is going, that's all we'll have time for. So here goes. Let's do another one. Let's suppose that there's an old drug. And in this old drug, the percentage of people who got better using it was 75%. So you've got some serious illness, and if you take this treatment or this drug, 75% of you are going to recover, and unfortunately 25% don't. And some pharmaceutical company have came out with a new drug. And this new drug had an 82% success rate. So we are looking at, is there enough evidence to prove that this new drug is correct? That they are a better drug than no drug? Now, the way the FDA people are going to look at this is they're going to say, okay, you got to prove it to me. Well, that in itself isn't proof yet. You have to go through the entire process, the hypothesis test, and at the end, we might have proof, that's great, or it might be not enough evidence, that can also happen. So we need some more information about this. Let's suppose that there was 200 people in the sample. So it was a nice random sample, check. The sample's big enough, check. The population is large, for sure. There's probably thousands and thousands of people with that disease. So stage 1 is kind of done, even though I'm not writing it. In this question, right at the beginning, there's a significance level. And let's make this particular one 5%. So as a decimal, 0.05. Okay. So we're looking now at setting up. So 1, we kind of talk through. Step 2, let's set it up. There's going to be a null hypothesis and there's going to be an alternate hypothesis, right? The null hypothesis is nothing's changed. The new drug's just as good or as bad as the old drug. And the alternate is that it is better. Whoops. Focus. It is better. You notice it's the same number in each case. The first one is always equal to, it's equal to whatever the start was, right? And the second one is what we're hoping to find evidence for. So P is greater than this number, P is less than this number, or P is not equal to this number. That's the only choices that alternate has. And the null doesn't even have a choice. It's always P equals whatever they tell you in the story was what it used to be. It used to be in the past, this number, that's what P equals goes here. We're now going to calculate all these various statistics. I've already got the p-hats, I'm just rewriting that down. I'm going to get the standard error. This time I'm going to try and make sure that I actually use the right number. I'm going to use 0.75. 1 minus p is 0.25, and 200 people. So I have square root of 0.75 times 0.25 divided by 200. And that comes out as 0.031, roughly. So that's that fella done. We then move on to step 4. Oops. There's 3. This was 3. Now we move on to step 4. And in step 4, we're going to get the z-score and the p-value. So our z-score is going to be our p-hat, take away our p-naught, all divided by the standard error. So in this case, we're going to go 82, take away 75, divided by this guy. Do that on my calculator, remembering to put the brackets in. 0.82, take away 0.75, divide everything by 0.031, and I get the number 2.258. Okay, I'll just do a little quick pause there. Are we happy about how to set up the hypothesis? That's this step. And how to calculate the standard error, which is this step. And how to get the z-score, which is this step.
I have a quick question.
Yes.
I'm sorry, I was writing when you started talking about the alpha being the 5%.
Yes.
How did you get that? Where did that come
They
from?
have to tell you in the question.
Okay, perfect. Thank you.
Yeah. So we're good up to this point. Right, p-value. I want to know what's the probability of getting a z-score bigger than 2.258. Can you hear me? Oh, things paused for a second there. Don't know if it was just me or you. Right, so we're looking at this fella here. It's either going to be the probability that z is greater than a positive number or z less than a negative number. Because sometimes the z-score can be negative as well as positive. If you're a visual kind of person, we're kind of looking at a little guy over there, right? So it should be small. For speed, I'm doing the same thing as I did on the main calculator. You're just not going to see me do it. So I'm in normal CDF right now. I'm typing in 2.258. Then I'm doing 999. And then I'm doing 0, and then I'm doing 1. And I have as my answer, hopefully you get the same as me, 0.012. And now we're ready for conclusion. The final step. We do our test. And we check, is the significance level, right? Let's get this right. Is P less than alpha? Is our guy less than 0.05? Or if you like, is 1% less than 5%? And the answer is yes. So is P less than alpha is our check, our test. And we managed to get a yes. So conclusion time. There is enough evidence to reject H0. And so HA is true. Well, that's what you say in statistics. In English, you could say there is enough evidence to prove the second drug is a better drug. Why is it better drug? Because, well, it's 82%, like it's larger than a larger success rate than the previous drug. So when they are conducting clinical trials, this is essentially the bare bones of how that is analysed. So when they send in the results for the FDA to approve the drug, one of the requirements is that the FDA has lots of, but one of the major requirements is that you have to prove to us that this new drug does a better job than the old drugs that are out there. And there's a couple of good reasons for that if you think about it. If you've got a number of different drugs that all do the same job, and they're all pretty much, give or take, equally effective, the problem with having too many drugs that do the same job is that there is more opportunity for side effects because there's now more drugs that you could have side effects with. Secondly, do you know when people take more than one medication, each medication on its own is probably pretty safe for most people. But unfortunately, sometimes when you put both drugs together, the combination of the two is like a lethal cocktail for a few unfortunate people. So to try and reduce the number of possible combinations out there, they make it simpler. There are financial reasons. Do you know a brand new drug's going to probably cost you 5 times or 10 times more than the old drug? So financially, it's much better not to introduce a new drug unless it's significantly better than anything that's gone before. Because all you're really doing is increasing the cost of care without any significant increase in